Okay, today we're going to learn about the definition of derivative. This is our next main unit in calculus. So in this unit, you're learning what a derivative is, how to find it using the definition of derivative, how to find the slope of the tangent line, and the relationship between differentiability and continuity that we learned in the last unit. So start with mainly a definition. Let's explain what we're talking about. So we'll often be asked in this section to find the slope of a tangent line. And so what is a tangent line? Well, before we can answer what is a tangent line, because a tangent line intersects a graph at one point. And how do you find a slope when you only know one point? So what we do is we approximate the slope of the tangent line by looking at the slope of the secant line. Because a secant line is a line like this one that intersects the graph at 2 points. This purple line would be my secant line. Okay, and passes through the point of tangency, which I'll let this point P here be our point of tangency, and it's at the point C, F of C. Okay, and then we have this other point. Now, with what we're going to do is this other point is going to be close to C, but just a little bit off. So we're going to say that this point is at C plus delta x, which is just a change in the x. So increase in the x by a little bit. And therefore, our function value, our y value, is going to be our function evaluated at c plus delta x. And so that's going to be the coordinate of this second point. And if you remember from college algebra, to find your slope of any line, you take rise over run. So we've risen up, or we call that change in the y, over our change in our x. Okay, now the change in the y is equal to our ending y value minus our beginning y value, and our change in our x is our ending x value minus our beginning x value. Now notice this one, c minus c cancels out, and that just becomes delta x. So change in x. All right, and then again, slope, and this is the secant line, is equal to our change in our y over our change in our x. So our slope of our secant line is going to be f of c plus delta x minus f of c over delta x. Now, often we will use in practice the x variable, x plus delta x minus f of x over delta x as a slope of our secant line, and then work from that to find our exact slope. So notice the right-hand side of this equation is what we call a difference quotient. That's the right-hand side here, okay? And the denominator, delta x, is read the change in x, how the x has changed. And the numerator, delta y, f of c plus delta x minus f of c, or f of x plus delta x minus f of x, whichever way you want to look at it. Again, I think sometimes it's easier to do with the x. Okay, that's an x. Okay, is the change in the y. Okay, now, what's cool about this is we found the secant of this tangent line. But if I slowly take this change in y here, so let me erase this for a second so I can draw on this picture. If I slowly move this delta, this second point closer and closer, and keep going, and move that second point closer and closer, and do that drawing of that line, closer and closer to this point that we're looking at, the point of tangency, because we actually want the tangent line. So we want to figure out the slope of, our goal is to figure out the slope of the line tangent to the graph that intersects the graph at exactly 1 point and only 1 point. And what we're doing is we're using these different slopes of the secant line to approximate, getting closer and closer, and we just keep moving that point closer and closer and closer until we can get pretty darn close and start approximating the actual slope of the tangent line. How do you get extremely close? Limits. We're going to take the limit as we do this. So using our knowledge from last chapter, we can say, okay, well, I could therefore take this knowledge and move that second point infinitely close to that first point by doing the limit. So I can find my slope of my tangent line by taking the limit as the change in the x value approaches 0. So as it gets infinitely close to that point of tangency of my slope of the slope of my secant line. Okay. Now, what does that look like mathematically? Well, that looks like the limit as delta x goes to 0 of f of x plus delta x. Oh, I use c and then I use c up here. F of c plus delta x minus f of c divided by delta x. Okay, and that has to be on some open interval. So by limits, we have to have an open interval to look at. And so we can approximate this value here. And that limit as the change, the delta x approaches 0 of our change in y over change of x is what we call the slope of the tangent line. So that gives us our slope of our tangent line. Okay. So this is the slope of the tangent line to the graph of the point f at the to the graph of the function f at the point f, comma f of c. So this formula is used to find the slope of the tangent line of the graph of f at the point c, f of c is also called, sometimes you'll see it referred to as the slope of the function or slope of the graph of the function. At the point x equals c. So if I ask you to find the slope of the function at x equals 5, then this is a process that you could use. So let's try one. Find the slope of the line tangent to the graph of f of x, if f of x is equal to x squared plus 4x at the point 1, 2. So our formula, slope of tangent line, is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. All right, so let's substitute in what we know. So f of x is x squared plus 4x. So f of x plus delta x would be x plus delta x squared, because f of x is x squared, plus 4 times x. So I'm going to replace that x with x plus delta x. Okay. And then we need a minus f of x. That becomes minus x squared plus 4x divided by delta x. So the limit as delta x goes to 0, x plus delta x squared, remember that's x plus delta x times x plus delta x, so that's x squared plus 2x delta x plus delta x squared. Now I'm putting that in parentheses because that's delta x times delta x, not delta x times x. So it's delta x squared. So make sure delta x is considered a variable. It's like a y. It's another variable. Plus 4x. That's also the reason why I didn't combine this. 2x delta x is writing it as 2 delta x squared because that's wrong notation. These are separate variables. And then plus 4 delta x. Okay, so that's simplifying the green. And then the red, all I got to do is distribute my negative. And then it's still all over delta x. All right, so now I'm just going to start combining, so I'll stay in one color. All right, so we got x squared and negative x squared cancel out. Negative 4x and positive 4x cancel out. We don't have any like terms here, so we got 2x delta x plus delta x squared plus 4 delta x divided by delta x. And then, again, if I do direct substitution, this limit at the very beginning, I got the indeterminate form of 0 over 0. So that's the reason why I have to keep plugging this in. And so we're trying to just simplify this. So let's see. All of this on top has a delta x in common, so I can factor out one of the delta x's. And then I can cancel out those delta x's. And I have the limit as delta x goes to 0 of 2x plus delta x plus 4. And then direct substitution in. I got 2x plus 4. Now, I wanted to figure out, but looking at our problem, we want to figure out this when x is 1. So I want to know when x is 1. So I'm going to plug 1 in, and I get 6. So the slope of my tangent line at the point where x equals 1 is 6. There's your slope of your tangent line. So that's how you use this formula, the definition of derivative, find your slope of your tangent line. We use the limit definition of derivative to find the derivative of a function. And so I'm going to start introducing a little terminology here. So you can arrive at a crucial point in calculus. Now, I always like to say calculus is divided up to 3 sections. Limits are the foundation of calculus. That's what everything is built upon. Excuse me. Limits are the foundation of calculus. That's what everything's built upon. And then the walls of calculus, the house of calculus, is made up of derivatives. And then the top of calculus, the roof of calculus is like integrals. And then you get all the fancy stuff. It's the decorations inside. So we're learning the walls that builds the house of calculus, and that's the derivatives. So one of the fundamental operations of calculus is derivatives. And this is a big unit. We'll spend the next 2 units talking about this. All right, so we're going to start by defining derivatives, which we're already worked it toward. The derivative of f at x has the notation, one of the notations is the derivative of f of x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x, or the limit, or the derivative is equal to the slope of the tangent line, because we just learned that formula to represent the slope of the tangent line, provided, of course, that limit exists. Okay. For all x for which the limit exists, the derivative is a function of x. The new function, this new function gives the slope of the tangent line. Of the graph of f at the point x f of x. Provided the graph of the tangent line, there's a graph, the graph has a tangent line at that point. This derivative can also be used to determine another terminology instead of slope of the tangent line, instead of the word derivative. Sometimes you'll use this especially in science fields. In physics, you'll use this a lot. Instantaneous rate of change. Or for short, sometimes it's just called rate of change. If they ask for the average rate of change, they're asking for the slope of the secant line, where you don't take the limit. And they ask for the instantaneous rate of change or just rate of change. They're looking for the slope of the tangent line, which is the limit of the slope of the secant line. So you do this formula here. All right, as you notice, I introduced one new notation for derivative, f prime of x. That's the the derivative of f of x, sometimes read f prime of x. Another very common one that we'll use throughout the year is dy dx, and that's the derivative. It's read the derivative of y with respect to x. Other ones that you'll see is the derivative of the function f of x with respect to x. That can be written like this. Or the derivative of derivative of y with respect to x, and sometimes you'll see it like this. So those are just some notations that mean the same thing. It's kind of interesting. We have a lot of notation that mean the same thing in calculus, mainly because it was being developed by a couple of people at the same time, and they use different notations. And some notations work better in certain situations that it was developed for. Other notations work better in other situations. So you'll see us change in between those. So basically, the derivative of y with respect to x is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x over x, which is also equal to the derivative of the function f of x. Okay, so that's two different notations for the derivative, just so that you can see those are the two most common that we use in this class. And that formula, I think I've written that like 5 times now, so it's probably a very important formula to memorize for the definition of derivative. All right, example 2, we're going to find the derivative of a function f of x equal to 1 over x minus 2 using the definition of derivative. Okay, so again, the definition of derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x over x. Okay, over delta x. I lost my delta x up there. Woo! I hope y'all were screaming at the video telling me that I had lost that. All right, so our derivative is going to equal our limit as delta x goes to 0. And I'm going to go to my function. Where I see x, I'm going to plug in x plus delta x. And then minus my function, just copy down, over delta x. Now, if I do direct substitution, I got 1 over x plus 1 minus 1 over x plus 1, so that's 0 over 0. So this is the indeterminate form of a limit, so we have to simplify it down. This is a compound fraction. And so we learned that method that we just tested over is we need to find a common denominator. So my common denominator is going to be this. Let me give myself a little more room. That's getting kind of smushed in there. My common denominator is going to be this. So the first numerator I changed by multiplying 1 by x minus 1. And the second numerator I changed by multiplying x minus 1 by x plus delta x minus 1. Delta x. So the limit as delta x goes to 0 of x minus 1, distributing that negative x minus delta x plus 1 over x plus delta x minus 1, x minus 1. And if I divide by delta x, and I flip that and make that 1 times delta x, multiplying by that extra dividing time, when you just have one thing on the denominator, it just stays in the denominator, the new fraction. So I can just write it like this. Well, let's see if I can simplify this down any. X minus x, negative 1 minus 1. And then I just have one term here at the top now, so delta x and delta x can cancel out. So I'm left with a negative 1 on top. Over x plus delta x minus 1 and x minus 1. All right, so plugging in my 0, that gives me x plus 0 minus 1. So that becomes 0. And so that gives me an x minus 1 quantity squared. So my derivative, the equation that represents the slope of my tangent line at any given point on my graph of f of x, is negative 1 divided by x minus 1 quantity squared. how to find the equation of the tangent line at that given curve. So let's say I asked you to find the equation of a tangent line at a given point. So you're going to do pretty much what you're going to do. You're going to find the equation of the derivative. So the equation of the equation for the slope of the tangent lines at any given point, then plug in the given point, and then that'll give you your slope of your tangent line. So we're going to find the slope of their tangent line by finding the derivative at the given point. Okay, so what we've done so far. And then this is the new step. We're going to use what's called the point slope form of the equation. Y minus y1 equals m times x minus x1, when m stands for our slope, and y1 and x1 comma y1 is the point given, to find the equation of the line. So let's try an example like this. Let's choose a new color. All right, find the equation of the line of the tangent line to the graph of this f of x at this point. So start by finding f prime of x, the derivative. And so that's my limit as delta x goes to 0 of f of x plus delta x, that's x plus delta x minus 1, minus f of x over delta x. Again, direct substitution gives me 0 over 0, so I have to simplify this out. And so the best way to do this is the rationalizing technique, where I'm going to multiply the top and bottom by our conjugate of our radical. And so doing the full method on top, I get the limit as delta x goes to 0 of x plus delta x minus 1. The two middle terms cancel out. Minus our x plus 1, because I have to distribute, it's minus that x minus 1. And then when you distribute, minus 1. And when you distribute that, it becomes try this one more time. It becomes negative x plus 1 all over delta x. All right, so x and negative x cancel out. 1 and positive 1 cancel out. Okay, oh, all over delta x times, I forgot my other part of the bottom here. Square root of x plus delta x minus 1 plus square root of x minus 1. All right, and then the delta x's cancel out. So I got the limit as delta x goes to 0 of 1 over the square root of x plus delta x minus 1 plus the square root of x minus 1. All right, now we can do direct substitution in. And I end up with 1 over square root of x minus 1 plus square root of x minus 1, or 1 over 2 the square root of x minus 1. So that's my derivative. But I want to figure out the derivative at the slope of the tangent. So my slope of my tangent at that given point is evaluating my derivative at the point when x is 5. That's square root of 4, so that's 1/4. Okay, because square root of 4 is 2, 2 times 2 is 4. So that's the slope of my tangent line. So now I know my slope of my tangent line at this given point is 1/4, and the point that was given to us was the point 5 comma 2. So to find the equation of my tangent line, I use the form y minus y1 equals m times x minus x1. Why this is my m, this is my x1. And this is my y1. Sorry, I had a sneeze. So I get y minus 2 equals 1/4 x minus 5. And then what you're going to do is solve for y, get those y equals. So to get rid of this, the fraction, the parentheses, and then move the 2 over. So I'm going to add 2 to each side. I'm going to choose to write that 2 as 8 over 4. And there's the slope of my tangent line at that given point. Last lesson I want to learn in this lesson is the relationship between differentiability and continuity. So basically, one way to help us do this is we're going to learn what's called the alternate limit formula form of the definition of derivative. And basically, instead of defining the points as we did in the first example, I'm going to find this bottom point as the point c comma f of c. So that's not different. And I'm going to call this top point x and f of x. And so again, slope is our rise, which is our change in y. So in this case, our change in y is going to be f of x minus f of c. And then our run across, which is our change in our x's, which is going to be x minus c. And so again, slope of the tangent line, or our derivative, I think I used the word derivative up here. So our derivative is going to be equal to the limit as delta x goes to 0 of the change in x over the change in y. Okay, and our change of x this time is change in y. Y is overrun. I don't know what I'm thinking. Change in y here is f of x minus f of c. And our changes in our x is x minus c. And we want as delta x goes to 0. But we got a problem. This has delta x, but we in our new equation we have x and we have c, but we don't have any delta x. So what we have to do is we have to rewrite this statement over here. So we have defined delta x to be right here, x minus c. Okay, and we want delta x to go to 0. So we want x minus c to go to 0. Maybe it's better if I write like that. So we want x minus c to go to 0. So that means we want x to go to c. Solving that equation for x. And so this form, instead of saying delta x divided by 0, we write x goes to c. And that is the alternate form of the definition of derivative. The limit as x approaches c of f of x minus f of c over x minus c. Either one of these are equally good. Some equations it's easier to work with the alternate with this form, and some equations easier to work with the original form I gave you. So just applies. Whichever form you're using, you'll get more experience as you work through it. Now, when we talk about differentiability, one thing's going to come up important, and that's one-sided derivatives. The derivative from the left and the derivative from the right. Just like we had the limits from the left and limits from the right, we're going to have derivatives from the left and derivatives from the right. So our notation for that, if I wanted to find left hand or our left hand derivative, I would use, if with the f of f prime notation, the derivative of f with respect to, let's say, c from the left, we put a little minus sign. And if I want to find the right hand derivative, that is f prime of c to the right. Now, this is the same formula. Let me use this alternate form up here, except if I'm looking at the formula I'd plug in for the derivative from the left, I would take the limit as x approaches c from the left of f of x minus f of c over x minus c. And likewise from the right with the right-hand derivative. So that's just some notation to know. So differentiability implies continuity. That is, if a function is differentiable, that means it has a derivative exists at c, then it is continuous at c. So if you know it's differentiable at a point, you automatically can assume it is continuous. And this come in handy later, so we'll say it's differentiable everywhere, so we know it has to be continuous everywhere. Or it's differentiable in this given interval, so we know it's continuous on that interval. But this is the key. The converse is not true. Just because it's continuous, it may or may not be differentiable. In fact, how do you figure out a function is not differentiable? These three things is what we look at. First, at any point, the function is discontinuous. And that's what we learned in the last unit. So if we have any if we have a point discontinuity, if we have infinite discontinuity, or if we have jump discontinuity, at those points that those discontinuities occur, it is not differentiable. Okay, if we have any sharp turns in our graph, okay, so any sharp turns in a graph, it is not differentiable. The reason why it's not differentiable, if you think about the absolute value graph, okay, the absolute value graph is not differentiable at oh, you can't see that color. It's not differentiable at this corner here. That's a sharp turn. Just think about it. The slope of the tangent line here is the graph is going down, so my slope is negative. My slope here, my graph is up, so my derivative from the left is not equal to my derivative from the right. So just like with limits, in order for it to be continuous, the limit from the left had, in order for the limit to exist, the limit from the left had to equal the limit to the right. So if the limit that the derivative from the left is not equal to the derivative from the right, then we have a sharp turn, and it is not differentiable at that point. And then our next thing we look at is it is not differentiable if we have something called a vertical tangent line. And that's graphs that kind of go like this. And then if I wanted to find a tangent line at this point here, my tangent line, it intersects the graph only once, is actually a vertical line. And we've learned previously that the slope of vertical lines do not exist. They're undefined. And so since this is a slope of a tangent line, this also has a, their slope does not exist. And so our tangent line, so our derivative at that C does not exist. So we would get undefined, limit, infinity, negative infinity, any of those. And that is the three ways to figure out if a function is differentiable or not. So looking at this graph, you can figure out any points in which the function is not differentiable. Let me zoom in so you can see these numbers here. So at this first one, if I'm looking here at 1, x equals 1, this is an example of that vertical tangent line. So at x equals 1, it is not differentiable because the derivative at C does not exist. There's no slope to the tangent line. So the slope of the tangent line does not exist at that point. Okay. And then the next one we can look at is B here. Looks like 3, negative 3. So at x equals negative 3, it is not differentiable, and that's because it is not continuous. And we know it's discontinuous because the limit as x approaches negative 3 from the left of f of x is equal to negative infinity, and the limit as x approaches negative 3 from the right of f of x is equal to infinity. And that's how we knew we had infinite discontinuity. All right, and then the third one, we have a sharp turn here. So at x equals 2, it is not differentiable. And because the derivative from the left of 2, not C, of 2, the left of 2 is not equal to the derivative from the right of 2. Now, algebraically, how would we do this? So we're going to determine if the function f of x, this piecewise function, is differentiable at x equals 2. First characteristic, it must be continuous. So we're going to show that f of x is continuous at 2. So we know x squared plus 1 and 4x minus 3 are polynomials. They're continuous everywhere they're defined. So the only possibility point of discontinuity is at 2. So the limit, so first let's do, I'll do in the order. F of 2 is 2 squared plus 1. That's 4 plus 1 is 5. So our function value exists. Our limit as x approaches 2 from the left, that's the top equation, x squared plus 1 gives us 2 squared plus 1, which is 5. And the limit from the right is 4x minus 3. So that's 4 times 2 minus 3. 8 minus 3 is 5. So therefore, our limit as x approaches 2 of our function equals 5 and exists. And so it's continuous. Since the limit as x approaches 2 of f of x equals 5, which is equal to our function value at 2. All right, so we proved continuity. That's step 1. Step 2 is now we got to show differentiability. And all you need to show differentiability is I need to show that the derivative from the left of c, or whatever our c value in this case is 2, has to equal our derivative from the right. So we want to find our derivative of c, our derivative of 2 from the left. Okay, I'm going to use the alternate form. So that's the limit as x goes to 2 from the left of f of x. So f of x this time from the left is going to be the top equation minus f of c, or f of 2. So 2 squared plus 1, we already figured out to be 5, divided by x minus our c. Excuse me, I keep coughing on this one. All right, so simplifying that down, I get the limit as x goes to 2 from the left of x squared minus 4 over x minus 2. That's the limit as x goes to 2 to the left of x minus 2 times x plus 2. That factors out, or simplifies down, get x plus 2. And that's 2 plus 2, or 4. So that is what our derivative from our left is equal to. And then we need to find our derivative from the right of 2, which is our limit as x approaches 2 from the right of f of x minus f of 2 over x minus 2. All right, so f of x from the right of 2 is 4x minus 3 minus f of 2, which we already figured out to be 5. We already did that work, so I don't have to show it. So the limit as x approaches 2 from the right gives us 4x minus 8 over x minus 2. Factor out of 4. The limit as x goes to 2 of 4 is just 4. And that is our derivative from the right. And notice that the derivative from the left was 4. And the derivative from the right was 4. So since they are the same, we can know that this function is differentiable at x equals 2. If I had gotten at any point does not exist for infinity, we would say it is not differentiable because of vertical tangent line. If I had gotten that the limit from the derivative from the left is not equal to derivative right, we'd say it's not differentiable because of a sharp turn. And if I got when it's not continuous, it's not differentiable because it's discontinuous at either a point discontinuity, infinite discontinuity, or jump discontinuity. And so that is it. That's this is our next lesson.